Hello. What I want to talk to you about is how we process some of these BBR specimens. If we look at bending beam rheometer, the standard test, we quite often will be making these little specimens up in the laboratory, and this shows an example of making these specimens in the Asphalt Institute lab during one of our RHEA courses, where you produce these beams and you can see the technician holding the beam there, and then you place them in the bending beam rheometer. And from this, we generate a test file. Now the question is how do we process this test file and to produce analysis of the data in an efficient way? And I'm going to show you this in the Weir software. So sitting over here on my desktop, I have three lots of testing from the bending beam rheometer done at 2 replicates for the 3 temperatures. And I'm going to start my analysis by just exporting this data from these tests into a CSV file. And I'm just going to show you how this is done. So I have a version of the Canon software on my computer, and if we load the Canon software up, we can basically do what's known as a batch export. So the batch export, if I select all the data files I have on my desktop, and I'm going to export those, it's going to export them all to a comma separated value file, and I hit the export button, and you'll see as it does this, it will generate these files. So close the Canon software down now, and I have an Excel extension association here with a CSV file, so I'll just show you what these files look like in an Excel spreadsheet, so you can see what information's in there. So the Canon, when you do an export from the Canon data, you'll have some information regarding a project, an operator name, and then you'll have things like the temperature, the beam span, beam width, etc. And importantly, you also have this information on the force and deflection, and I'm just going to, this is what we see from the Canon rheometer, and very quickly, just to show you what's there, this is showing how the force varies with time. I'll slide this over one further. This shows the deflection of the beam with time, and the fourth column is the temperature with time, which is effectively constant. You can see it varying there by 0.02 degrees at the most. So what we do is we're going to bring this into the Weir software, and we're going to analyze this in the Weir software. So I'm not going to save this, I don't need this. I'm going to kick up the Weir software, and I have that icon saved down below. So here comes the Weir software. We'll just let that load. And this is the version that's been released in June, July 2022. So I go into here and I go with a file, and I want to do a preparation and to make the RHEA format from the raw data file. So when you load the software up, it comes up with a blank screen. I'm going to hit the raw button. The raw button here will allow me to load the data files from a machine in. Now, in this case, I've got it set on Canon, but if you hit the pull down menu here, you'll see there's various options for different manufacturers' equipment. And we're constantly working on making sure that we can analyze data from the different equipment. So we're working with formats which are exported from equipment and then we can analyze them. So anyway, selecting the data here, I can basically, using my shift key, select all those data sets. These all correspond to a Canon CSV format, and I have to make sure I've got that set here to bring in the right data set. So I hit the open button, it reads those files in, and you can see it's made a plot here of apparent stiffness on the vertical axis versus loading time on the horizontal axis. And you can see here we have two replicates for each temperature. Now some of you might decide that this 6 degree C replicate is too wide apart, these other replicates are fairly close together, but I'm going to leave that as it is now, and I'm going to go through my parameters I want to set here. I'm going to leave my units as megapascals. Density of the binder 1.02 is a good idea. I'm going to put my title of my file as example BBR. As I said, the units I'm going to leave as MPa, density at 1.02. The reference temperature, I can choose any temperature between the highest and the lowest. I think I'm going to accept the lowest temperature here, so I'll put -12. The glass transition temperature, that's really an estimate of where we think the glass transition might be, and it affects these expansion coefficients. I normally use 0.3017 below the TG for an asphalt binder and 3020 above the TG. We have to remember that TG is not a very precise fixed point with an asphalt binder. It's probably more over a small range. Because all of this testing is above where I'm anticipating the TG to be, the expansion coefficient of 0.302 will be used in the analysis. A couple of other things here. This distortion limit applies only to DSR testing, so will not affect anything I'm doing. And I'm going to merge isotherms that will within a 1 degree C tolerance. So it will basically take the average of these isotherms. So this is all okay. I hit Save TTD. It asks me for a file name, so I'm going to call this example. And it saves that to the desktop. So I can hit OK. If I look at my desktop, you will see it's made two files, one called example. If I open that up, this is the format that's used within the Weir software. It's got the three isotherms all averaged, a control line and the title line that I gave it. This other file is a statistical information file, and it contains information about where that data came from and whether it's valid, etc. So this other file, this STI file, is basically a history type file of that information. So I'm going to close both these down for now, go back into my Weir software, and this file is now in a TTD file, so now I can read that in. TTD stands for time, temperature, domain analysis, and when I read that file in, I'll get a very similar plot to what we saw previously, but instead of 2 lines for each isotherm, you'll see that they've been merged into a single line. I can now look at the master curves for these and the information I have. This gives you the shifting that's been done by Gordon and Shaw, the pairwise shifting method, and there's various information we can look at here. We can look at the quality of the master curve. Very simply, this is the discrete spectra fit and the master curve that's been produced here. And you'll see that there's various master curve formats that are available. We can look at the Christensen Anderson information. We have a couple of versions of Christensen Anderson, one for the S of t, one for the E of t, and we also have the reciprocal of it, which is in effect the D of t. most folks will probably be interested in this type of plot for the Christensen-Anderson, where you have the standard output information, including the R value, the root mean square of the fit, and this assumes a variable glassy modulus and a variable kappa value in the equation there. So that's some information that we have. If we flip on to the next tab and we hit this hammer, the idea of the hammer is it's a quick analysis, is we can get some idea of the delta TC data. So this is showing you the delta TC calculation, and you have the various information associated with that calculation in this window over here. So here for this particular binder, it's calculating a delta TC of 7.49. One thing I should point out when we look at this, the data set and the data that's going into this analysis, is typically with a bending beam data set, we normally will see 6 data points being used. But because we're analyzing this data in an automatic way, we feel that it's more of a robust analysis if we obtain 11 data points. So you'll see each of these isotherms is represented by 11 data points. And because we're working with a raw data file from the equipment, we can just extract intermediate data points very quickly from that data file, and it provides a better time temperature shift when we produce a master curve. So the master curve, which we look at in terms of pairwise shifting, we get a more robust shift and we get more data points overlapping when we use the 11 data points for each isotherm versus the 6 data points. And in fact, the recommendations by Gordon and Shaw are that we make use of a minimum of 5 data points per log decade of frequency, and by using this additional data point, we basically are then conforming to the recommendations of Gordon and Shaw. The other thing that we can do very quickly is using a assumed Poisson's ratio. We can convert this data, which is in a bending format, to a shear format. So I can hit the convert here. It's saved 2 additional files to my desktop. So if I come over here and I look at these, the desktop, you'll see it's made an example file here and an example file here. And I can load these files up. So I can load the, in this case, I'm going to load the G file up. This is now converted to something equivalent to dynamic shear data. And we can see master curves in a similar way, modulus and phase angle. And I can look at this type of data, E prime, E double prime. I can look at it in a black space. And this allows me to merge that data with a dynamic shear data. I'll leave that subject for another video where I talk about merging dynamic shear data with bending beam rheometer data. Bending beam rheometer data is very useful for evaluating the cold temperature end of the master curve, and it's a useful way of providing some checks to what's going on in the data set. And that's pretty much what I wanted to show you here, how we take the data from a bending beam rheometer. We can very quickly analyze that data to give us the Christensen-Anderson plots. Things like the R value are of great interest to folks today. We can also go and get items such as the delta TC, and this window here also gives you the pass and temperature for the stiffness. So here we can see the temperature where the stiffness passes. For this example is is minus 19. The temperature where the M value passes is minus 12, and the delta TC is minus 7. So very quickly we can get the PG evaluation from low temperature testing in the bending beam rheometer without having to do anything in a spreadsheet or any manipulation, and it's a very accurate data analysis. So with that, I'll say thank you very much for listening to this video, and please look out for more videos in the weeks to come. Thank you.